In a previous CPD, someone made a request for the topic of multiplicative reasoning to be covered. So I focused on this very much specifically in the first half of this presentation. I believe this topic evolves very closely to algebraic reasoning and to something that we use at my school, which in the second half of the presentation I want to showcase and share. It's very important before we can move on to a lot of advanced topic that involves ratio to understand what multiplication is. But multiplication opens doors to so many different topics, and not just being able to do multiplication, but to understand it and to understand when it is used. Feel free to use this video in its entirety, or to look at the first half on multiplicative reason, or look at the second half, which looks very much at my curriculum and how multiplicative reasoning develops into ratio and is used in many different topics. So, if I'm going to be throwing around the word multiplicative, I think it needs a definition. And I did go to the internet and looked at multiple different dictionaries to see how it's defined, but I'm going to state one here, relating to multiplication. Fairly obvious. But in this dictionary, and I'm not going to name and shame, they have brackets afterwards, equals the process of adding a number to itself a particular number of times. Firstly, I object to the equal sign being used in that way. It's a terrible use of the sign. But more fundamentally, is multiplication always repeat addition? So here is a task, and I've taken it from a resource from NCET-M, the Maths Mastery, something I'd like to use more of with students that I teach. How do you say this expression? Draw a diagram to explain the meaning of the words, and compose a story to fit your expression and model. Some people may find this activity quite challenging in the sense that they feel it's simplistic and perhaps even beneath them. The intention of this activity is for students to appreciate that there is more to understand about multiplication than is often accounted for. Multiplicative reasoning, yes, it does relate to multiplication, but do we teach students to understand what multiplication really is? And if the answer is no, then maybe we should. How often are students unable to do a question simply because they don't know what operation or operations they need to do? I'd argue that there is maybe little merit in persevering with times tables or practicing multiplication algorithms if students don't know when to use them. I bet for this, the common phrase would be 12 times 3. But is there an opportunity to say the product of 12 and 3? A story might be something like 12 sweets are given to 3 people. What is the total number of sweets shared out? But could we challenge students, and could we offer the example of a line of 12 centimeters is enlarged by a scale factor of 3? How big is it now? Or 12 people in one class have a choice to pair up with 3 people from another class. How many pairs are there? These are clearly not repeat addition, although they can be forced to obey that model. They offer a real opportunity to understand multiplication and to reason in that respect. So, there was some research done, and I mean, it's quite dated, 1977, I've cited it here, but people were asked to write stories, a group of 11 to 12-year-olds, for these different calculations. And I wonder if you might take a minute to just think what percentage of students could do these for the different types of problems that are there. Students found it harder to understand and contextualize multiplication than division. It might be useful to consider the role that the research is playing. In my experience, most teachers believe their students will perform better than this. Is it always, sometimes, or never true that multiplication can be written as a repeated addition? We extend from natural numbers and integers to rational numbers and real numbers, and perhaps even complex numbers. How does this definition stand up? It's a wonderful article, and I really would advocate reading it. It's easily Googled, and you can read it in its entirety, and also read a lot of discussion that comes from it. But there's a real argument to say that if we sell multiplication as repeat addition and repeat addition only from the very beginning, we teach a misconception, and we teach a misconception then that is a real barrier for students being able to understand maths at a later point in time. The article actually advocates that you do not teach multiplication as repeat addition because it's harmful. I'm not saying we go that far, but I am saying that we do need to make sure that multiplication is understood in lots of different ways so that students can reason mathematically and apply it in lots of different circumstances. If our very first ideas in maths, if our very conceptual understanding is wrong, it becomes a barrier for us to move forward. So, coming back to the question of 12 times 3, all of these different diagrams represent 12 times 3 in some way, shape or form. And yes, you can fix them in many cases to be repeat addition, but the actual idea behind some of these tries to move away from that there is such a thing called scaling. There is proportionality involved. And proportionality is involved in the idea of multiplication, and especially when we're not dealing with integer values and we're looking at rational values and scale factors that may not be whole numbers, it becomes quite difficult to make it fix the idea of repeat addition. If you take one fraction multiplied by another fraction, for example, it's hard to force that into the idea of repeat addition. So early on, we need to make sure in our contexts for students, when they're first doing multiplication, that scaling is part of that. Scaling is part of that dialogue, and they're getting questions in that form, and they're understanding that multiplication is not just repeat addition, although that is one single useful way to understand it. You look at early maths in particular, the use of manipulatives, the use of ways to visualize number, and concrete ways to play with numbers using cubes. Dean's cubes is a good example, allow students to understand things. And when we start to move on, especially towards proportion, double number lines are a powerful way of doing that, to be able to see that one thing represents another thing, and the scaling idea becomes concrete in students' minds. I'm personally very guilty of showing techniques and approaches and I suppose algorithms to deal with ratio, but that understanding is really part of multiplicative reasoning that we have to do, and we have to know the types of diagrams to use to help students realize that. Bar models are another great example, just graphical representation, again, that's again very powerful. I know in all our curriculums, similar shapes will feature in some way, shape or form. Is it a topic, especially for a question like this, that needs to be taught if somebody understands what multiplication is. Obviously they need to know the word similar, but I would argue that numerical problems like this are just natural results because of multiplicative reasoning. Students will know 51 is 3 times 17, so it must be 66. I'm not saying not to teach the topic formally, but I am saying giving opportunities to understand and perhaps even draw questions that may later on be something we teach formally earlier on into our multiplication topics might help students to understand multiplication as a scaling process very early on. Earlier on, I gave a similar problem to make a story that represents the calculation, but I had 2 natural numbers there. Now I've got 2 rational numbers, and it's a lot harder. I think I commented that students might find the previous task almost insulting or beneath them, but this is a real challenge. How can you make a practical problem that represents this calculation? Perhaps, thinking off the top of my head, a smaller model of a 60 centimetre tall pot is made. It's 10% of the original pot size. What is its new height? Again, a really rich challenge and a very simple question to give, but something that shows understanding of multiplicative reasoning, and it's not repeat addition, it's scaling. So I'm going to take a minute just to give you the chance to reflect. Something as basic as multiplication that all maths teachers have been teaching from the very beginning. Has anything I've said already changed your view on what multiplication is? Changed your view on perhaps how we should teach multiplication and how multiplicative reasoning could be included somewhere in the schemes where we teach? So we've got a few ideas on multiplicative reasoning, and I've done some research on this, and I don't get much more than repeat addition and scaling, but the more you think about the maths we teach in our curriculum, the more ideas come up. So I'm going to perhaps move on from scaling to proportionality and go on a little journey of how multiplication can be thought of as different things at different times. Another way of understanding multiplication is the Cartesian product. In mathematics, specifically set theory, the Cartesian product of 2 sets A and B, denoted A cross B, is the set of all ordered pairs. This wouldn't be a way where multiplication is introduced in key stage 2 or 1, and therefore the actual understanding that finding combinatorics and combinations of things is a use for understanding multiplication. Easy to be lost. The idea using a GCSE style question is, if I have 3 main courses and 4 desserts, how many combinations of the meals are there? And do we know the answer is 12 because we understand this to be a multiplication problem? And yes, we can draw a table, or maybe we've learned a process, or we've learned that we draw a table. But are combinations in themselves a case of repeat addition, or do we manipulate the structure to become repeat addition in order for us to know what we're doing? Reflecting on my own mathematics journey, I remember finding combinations and permutations really hard in school as part of my A-level course. I still find the topic. I lack confidence in teaching it. Is this because understanding multiplication as a Cartesian product was not something that was ever focused on in my early days of school? I remember binomial theorem, for example, is a very easy topic if I just follow a set of rules. If I'm asked to try and explain why choosing 3 from a set of 5 gives me 10 ways, without listing them, without using formulas, even now I find that really hard to demonstrate. I know some statistics teachers who can see a problem and they can immediately understand combinations and permutations with real clarity and really explain it nicely. And I think it's because they understand multiplicative reasoning, and that Cartesian product is a case of that. There's one more idea added to the list, but I still think there's more. I think we can really and truly understand multiplicative reasoning unless we know the grammar associated with it. And perhaps it's not just be able to define the words distributive, associative, commutative, but to actually understand them. I'm not so pedantic about the words being used, but the understanding. So in the first question, when a student sees 25 times 27 times 4, would they naturally do 25 times 4, group that, and then the 27, do they understand that associative rule really, really well? Second being a case of the distributive rule. If we're doing 7 times 35, that distributive rule is at the very core of understanding multiplication at primary school, splitting a number up, its ones and its tens. Students who don't understand that rule cannot move forward. And again, other number problems, 35 times 99 being 35 times 100 take away 1. This is again the distributive rule, but it's being used. And we need to give students opportunity to do number problems, because those number problems will generate into algebraic problems later. Looking at the first one, we've all seen students make this mistake. How much of this is a silly mistake that really seasoned mathematicians make? And how much of it is a result of the distributive law not being adequately practiced with numerical calculations? It is of my opinion that students who make mistakes like this one often make the mistake because they treat mathematics as a set of rules to be learned rather than a structure to be understood. You should never really need to be taught how to expand a single bracket if you understand what multiplication is and if that distributive law has been revealed in primary school and well understood. It is noteworthy that a double bracket expansion, such as the one also demonstrated here, is more of an understanding. It's actually combinatorics. Seeing that situation is a result of understanding that multiplication is a Cartesian product. We know when we expand two brackets that we will get 4 different outcomes that may or may not be simplified. In a similar way, expanding a bracket such as the one at the very bottom, for somebody who understands multiplication as more than repeat addition, it's quite easy. And I'm sure that you've had students in the past who are very able, who you've done expanding pairs of brackets, and maybe you've put an extension down to expand something like this, and that really gifted mathematician is just able to do it without being shown. And how can they do it? Well, it's because they understand that multiplication is more than just repeat addition. They understand multiplication. So our list is growing. And the reason why I'm showing you this list is because I'm hoping that maybe some people reflect on schemes of work and schemes of learning and think, where are these things taught? Not the process of doing it, but the skill of understanding it. Where is it in our curriculums? And can we refine our curriculums to include it? Not make up new topics, but find topics where we already use these things and use them as chances to help students practice and understand and reason mathematically. We want our mathematicians, when they hear the number 24, to appreciate how wonderful it is by making statements such as, that is 2 cubed times 3, or even, that number's got lots of factors. Equally so, we want, when a number like 29 is mentioned, for there to be an appreciation that it's prime. 27, being a cube number, has only one prime factor 3. We want mathematicians to see numbers and to understand that numbers can be written as a product. They can exist in that form, and in many ways that is the most beautiful form for a large number to be represented in, as a product. Multiplicative reasoning is central to us understanding what natural numbers actually are. So another beautiful problem, which I'm grateful for NCETM for providing, that could be assigned to schools of work. Obviously here we've got division being the kind of central element, but is this really a multiplication problem? Is understanding division as an inverse operation to multiplication part of our understanding of multiplication in itself? Before that, all division problems can be thought of as a multiplication problem, and in many ways with the use of fractions we do this, but this is a new layer of depth, is understanding multiplication as the inverse of division. I think I'd be doing this topic a great injustice if I didn't say that within multiplicative reasoning we must talk about our times tables and we must talk about algorithmic processes. I think our times tables help us understand what multiplication is, the very formation. And times tables rockstars does this very well. That forming multiplication as the inverse of a division is very, very important. Pupils are expected to know at some point 5 lots of 7 before doing their 7 times table, because in the teaching process commutative laws are there. The very first days of learning a new times table are by repeat addition, and often the very first recall of facts like 6 lots of 8 is a quick calculation from 5 lots of 8. When I was in school, I never met my 13 times table. Perhaps it was never taught, but knowing 12 lots of 7 and then adding another lot of 7 means I'm able to reason. Primary specialists should be, and usually are, masters of teaching for understanding in these early years. As secondary specialists, I'm afraid we need to also be masters if we're going to be able to support our weakest students to understand mathematics. It took me many years of maths to understand that each algorithm we teach students is not primarily focused on getting answers. It's not a competition about which algorithm is best. To multiply, to repeat addition. Therefore, it is wonderful practice at a point in time to add and add and add so that you understand multiplication. The grid method of partitioning hundreds and tens and ones is again so rich if it's taught for the right reasons at the right time. The Chinese method of making diagonal lines in boxes and then adding up diagonal lines, again wonderful, perhaps not for the process of doing multiplication, but for the idea of understanding multiplication and how place value plays a role in that. And yes, we do advocate this is a great tool for getting answers, but all of them contain opportunities for multiplicative reasoning. And of course our chief algorithm, long multiplication, gives us the deepest level of understanding of what is happening. But they are all just algorithms that can help us understand maths better. Equally so, knowing 7 times 8 to work out 70 times 80 is multiplicative reasoning. There is so much richness if this is focused as a tool to understand maths better, not just to get questions right. Coming to a conclusion of the first half of my presentation, how can multiplicative reasoning be taught better? Starting with number 3, our schemes of work and the curriculum we teach focused on procedures of multiplication? Or is multiplicative reasoning present in ways that which empowers them to train students to understand what multiplication is and in what types of situation it's needed? Are staff skilled enough and expert enough in their explanation to use diagrams and manipulatives to teach this? Some students may require input to what teachers of early years primary may traditionally offer. If you've spoken to me or have a look at my CPD and other topics, you will see a trend that I am an advocate of reducing the need for calculators in maths. This is not just a personal aversion, but something based on personal observation and research of others. Skill in manipulating numbers allows generalization and understanding in mathematics. I think I've cited enough educational research in my other videos to support this. I have not yet decided how radical to take this approach in my own curriculum. I certainly, with minor adaptations in the curriculum for trigonometry, can't see much use for calculators in year 7 to 10 and year 12. But all the same, champion number. Choose examples and exercises that offer opportunity for students to use multiplicative reasoning in number. To understand multiplicative reasoning at the beginning, you need to have things to play with, things to count. You have to see the mathematics to understand it. At a later date, arrays, bar models and double number lines are there to develop understanding. And then an understanding that a particular situation leads to multiplication will come. Eventually, this can be generalized into algebra. And this is going to be the focus of the second half of the presentation. Not something I advocate for all students or for all schools, something I think is wonderful and powerful, if and only if multiplicative reasoning is already good. Something that is supposed to be challenging and thought-provoking.
This is actually like a multi-place topic. I'm covering loads and loads and loads of stuff, but we're going to be looking at a range of topics using a unifying method. So that might be useful. You can watch me model it. I'm going to try and model it exactly as I model it in class. But obviously I'll be messier because I'm using my Wacom, and I'll be quicker. So the first question is, what single skill in year 10 is a good indicator on higher paper being accessible? Lots of solving equations, and in particular algebraic equations. And I think that is the key indicator as to if somebody's capable of higher GCSE. I think higher GCSE is really hard if somebody can't solve equations like this. And I personally would devote as long as is needed in our school at making sure people can solve equations before moving on, because so many topics will be unpleasant. So just to show how we do this method of cross multiply. I do it waving my arms in the air, and I show them that they can do one side, they can do the other side, they can flip them both. But generally speaking, an equation like this, the next line should be 13x is 26 times 6. And I'd really encourage that, and I encourage them not to work that out on the right side. Most of what I do today is non-calculator methods. We divide both sides by 13, and then you can see why the 26 times 6 wasn't a good idea to work out. We can see that cancels with 2, so we get our answer of 12. And you know, we in year 8 we put that unknown in lots of different places, and we make the unknown linear factors, and sometimes we might even string together a like this one down here, a cubic equation or a very simple quadratic equation. But you know, all of that is really good for their algebra. And when they can do that, and when we are confident they can do that, we can start to think about ratio problems. Now, when I taught this before, I actually used to hate currency and most ratio things. It was the new GCSE that kind of made me think about it more. I always felt that students didn't know whether to times or divide by the multiplier, and I felt I needed to think about it as well. So now I've got a way that is fail-safe in their margin, in their books, or on the exam paper at the left-hand side. They just make sure that they get their numerators and their denominators the right way round, and it doesn't matter which way round it goes, is equal to how many pounds can I get for 36 of the dollars were at the denominator, 36x. So now we solve that equation. Better mathematicians will just bring the 36 up, but especially at the beginning of year 8 when they do, I do encourage them to actually do that cross multiplication, and the better mathematicians just get better when the time comes. So we've got our x is 360 over 18 divide by x equals 20, and we write our comment at the bottom. So we're doing that in year 8, and I would promote that method for doing it after algebraic fractions. And we could do lots of different kind of practice of this same skill, which is all just practice of their algebra. 200 grams of box contains 24 individual chocolates. Sometimes I get them to think a little bit about which one goes on top and which one goes on the bottom, and it really doesn't matter. But if I put grams on top, I've got grams per chocolate. So it's a sensible way to set up my equation, because sometimes that division actually means something. Like if it was meters and seconds, we'd have something profound. But other times it's just a constant of ratio. So 200 over 24 equals 300 over x. We do our cross multiplication. 200x is 24 times 300. We divide by our 200. Divide by our 200. I was a bit naughty now, actually. I tell them to simplify this first. That was very naughty of me, I'm sorry. X is equal to, so 2 into 24 is 12 times by 3 is 36. 36, and then we write a comment anyway, but it's almost leading them up to when we are going to have harder algebra in the questions and trying to develop algebraic approaches. Grams, so that's cost per gram would be an interesting or useful thing to have. So if I put my pounds in there, it's 80 grams over 15. So that's x over 18. So 15, we go, 5 goes into 80 16 times, is that right? 5 goes into 80 10. 5, yeah, 16 times over 3 is equal to x over 18. So 16 times 18 is equal to 3x over 3 over 3. So 6 times 16, 32, 96. So yeah, x equals 96, and we've got that there. So it's keeping these methods. It's also good practice of their algebra and mental maths. I never really encourage calculator use, but when they do get to use a calculator, obviously the process is even easier. Same with recipes. So if we've got a certain amount of flour, so we've got grams per cake would be a useful ratio, grams per cake. So we've got 100 grams and make 15 cakes. So that's equal to 60 grams. And how many cakes does that equal? X is equal to 3 times 60, divide by 20, divide by 20, cancel, cancel, 3, x equals 9. So we've got our method and it's kind of working through. So now is where it starts to get a little bit controversial. If the method is really embedded in how students work out ratio, if they've spent a long time in algebraic fractions, they're very comfortable with it, a question like this they might tackle in a non-conventional way, and can I add probably an easier way as well. If you travel 4 miles in 6 hours, hours, 4 over 6, how far do I travel in 10 hours? X over 10. So you simplify your fraction. X over 10. 20 is equal to 3x. Divide by 3. Divide by 3. X equals 6 2/3. So I travel 6 2/3. If we do use the more traditional method of just speed is average speed is total distance traveled over total time taken, we would find that we're getting a multiplier which could then lead to us trying to work out a decimal or multiplying fractions or other things. So it does work out quite a lot nicer, and it works out nicer as well in density problems. Although, again, probably if I was modelling this to students in a GCSE paper, I would use the speed as distance over time and the density as mass over volume to try and really make those things clear. But I might give them the alternative approach by the side, and some of them do use that, and it is neater. It's just tidier. So I think there's an argument so far that most students who are who are going to do well at higher GCSE wouldn't have a problem with any of the questions up till now anyway. But this is where we get things where students get things wrong because the method they use is learning a formula. And if they don't learn the formula, or they mix the formula up, or they don't understand the formula, it goes wrong. But if we do sectors, so we'll do the length of this over 2 pi times 6 is equal to 60 over 360. We just have a simple ratio that we simplify. L over 12 pi is equal to 1/6. 6L is 12 pi, divide by 6, divide by 6, L equals 2 pi, and the units would be centimetres, and I'd probably encourage a comment with that as well. And exactly the same for our area of the sector. Area over pi times 6 squared is equal to 60 over 360. So no learning of a formula at all. It's just using a method that's well established and repeated time and time again. Over 36 pi is equal to 1/6. So 6a is equal to 36 pi, divide by 6, divide by 6. And yes, better mathematicians just bring that up there in one step. But we want something that's accessible to everyone. 6 pi centimetres squared. It's notable when we teach this then at A level, it all just moves into radians. So if we had, this was pi by 3, and this is 2 pi, you can see the pi's just cancel. So rather than remember the formulas that the length is r theta and the area is half r squared theta, we're not learning formulas, we're just understanding what we're doing. We're finding a fraction of a whole circle. So it lends itself well to the A-level content. Similar shapes, perfectly. One thing to note is with similar shapes, even if it's just a length one, do get them to go from one triangle to the other, and if necessary, draw them orientated in the correct way. These are, but if I go 3 over x is equal to 10 over 12, so 3 over x is 5 over 6. So 3 times 6 is 5x, divide by 5, divide by 5. X is equal to 3 times 6, 18 over 5 is 3 3/5. Oh, I can't write there because there's a little box on my work, centimetres. So it works really, really nicely with all. We go from one side to the other. 3 over 10 is equal to x over 6. So 18 over 10, the answer will follow through. 18 over 10 is equal to x. So x is 9 over 5. I still don't like using decimals, which is why I really push to use neat methods. So 9 over 5 is 1 4/5 centimetres. Okay, so now we're moving on to similar shapes one again, but we've got an area, and if we taught that already, usually the students are absolutely fine with it and they just immediately do this, which is actually what we want them to do. X over 5 is equal to 18 over 50, and this is exactly what they want, and we work it out with a shape, perhaps a square or something, or something they can work the area out, and we see that it's wrong and it's failed, and we can use a few different shapes to quickly get the idea that this one here is a squared. We were doing this here, so we get to the practice, and if we've done lots of these earlier on in year 8 in particular, we don't get any major problems with them simplifying their fraction. Think of a number, divide by 5, square it. The answer is 9/25. X over 5 is 3/5. We mentioned why we don't have to worry about negative things. Good students will just see the answer is 3, but just to keep following a system, other students might prefer to just complete it off and say X is equal to X is equal to 3 centimeters, and we check if it's sensible. So we can do those. We can do them for area. We can do them for volume. System. So we've got the same system for proportion. Now I'm going to, by the side here, give the traditional way of doing this and then our way of doing this, and then you can compare them. It took me a while to be a convert to this, but it really did. So the traditional way to say y is proportional to x. So then we let y equal kx. We sub in our point. 12 is equal to k times 10. We solve the equation, divide by 10, divide by 10. K is 6/5, which some students will try and make as a decimal. We then substitute that back into our original formula, 6/5x. We then would put in our point y, so y is equal to 4, which is 6/5x. We times by 5, 20 is equal to 6x, divide by 6, divide by 6. So x is equal to 10/3, and we would have our answer. Quite a lot of work, and I personally believe most people will make a mistake. If we use our simple method of before, and again, I get them in their margin just to put their y in x, just so that it doesn't matter which one's on top, which one's on the bottom, but 12/10 is equal to 4/x. 6/5 is 4/x. So 6x is equal to 4 times 5, divide by 6, divide by 6. X is equal to, cancel, 10/3. And I think it's quite convincing that it's quite a bit less work, and it works very nicely all the time. Students really do, when they learn the method, just find it's absolutely fine. You could say, what about when we have proportional to the square of? Well, it's exactly the same. I get them to write it in the margin just so they're reading it off, but 12/2 squared is equal to y/3 squared. So 12/4 is equal to y/9. 3 is equal to y/9. Y is equal to 27. So it's much easier than the traditional method. Sometimes it doesn't say what is y when x is. Sometimes it says write an equation in y and x instead of that, which is even easier. 12/2 squared is equal to y/x squared. So we get that value. 3 is equal to y/x squared. So y is equal to 3x squared. So it works just as easily with all cases. The only issue with teaching this method is when they're taught things in physics and biology where they use this little symbol here, they get lost in biology and physics and chemistry, and they ask us, and we kind of need to translate it into the way that they understand it. And I've added into our year 11 scheme of work a little note on just trying to decode that symbol, because they do need to know that symbol, because sometimes it is used in the exam, but they don't need to really add to it. So the method follows through very neatly with inverse proportion. If you look at the table above, the student should be very confident that these are directly proportional, and they can do 1/3 is the same as 2/6, is the same as 3/9 or 4/12, and they understand that this is a fraction. It's the x over y is equal to, say, 1/3. Or they could do the reciprocals of them both. If you present an inverse proportion, when one gets bigger, the other gets smaller, it doesn't take them very long at all to notice, it's the product of them. So it's xy is equal to 1 times 24. So xy is equal to 24. Y is 24 over x. And then you kind of give them that, oh, sorry, I can't write 24 over x. You get that general rule for students that we divide when it's direct proportion, it's their ratio is the same and their product is the same for inverse proportion. Carry on. So y is inversely proportional to x. So we've got in the bracket here, I would normally get to do yx inversely proportional. So 12 times 2 is equal to y times 3. Solve the equation, cancel, cancel 4. Y is equal to 8. So we get there very, very quickly. And if I was to do that by the traditional method, y is proportional to 1 over x. So we let y equals k over x. We sub in our points. 12 is equal to k over 2 times by 2. We get k is 24. So then we get y is 24 over x. We sub in x equals 3. So y is 24 over 3. Y is 8. There is no conceivable way that this method is in any way suitable for students if they can do algebraic fractions from an early date and they can solve those equations well. I mean, it's far too lengthy and mistakes will happen. This was one from our previous one, so I'm not going to go right the way through, but just to kind of give the idea that it's the same method used in all these different topics. So every time we practice the method, we get students becoming more confident and happier doing it, and then they solve the equation. So it's all a fraction equals a fraction and solve it. So now we're moving to topics that perhaps traditionally in the old GCSE would have been A-star topics. Why were they A-star topics? Perhaps because students have to manipulate the algebra or not see things. But if you use the idea of a ratio, we just get very quickly that sine A over 10 is equal to sine 63 over 14. We don't even need to teach them the formula, sine A over A, sine B over B. And we don't need to teach them as well, this is the form you do if we know an angle, this is the form. We don't. They're used to this and they're used to solving the equation. So if they can get to the first step, they're usually fine. Obviously, this one would need a calculator, so I will carry on. In year 9, our trigonometry comes directly after similar shapes for the exact reason that this angle is we're looking for a ratio, and the first examples in the scheme of work state to use 30, and then they can spot very quickly that 30 is a ratio of a half. So sine 30 is 5 over x. And again, it's absolutely fine them doing opposite hypotenuse and SOHCAHTOA and all of that. But it's this idea that a fraction is equal to a fraction, and that's how we solve it. This one we could work out as a fraction immediately because we know how to do it. So 5 over x is x is equal to 10. And we put some units in with a comment. But the method we've used just puts itself everywhere. Some students like to do this, notably, if it's a number, they just prefer the cross multiplication. If it's just a number, they like to put 1 there, and that's absolutely fine. We kind of hope that as time goes on, they'll no longer need that. Capture, recapture. I think this came across as being a high-level problem, but if you're good at solving equations and you can set these up, 30 out of the whole population are marked, and we recapture 5 out of 20. So we solve our equation. 30 times 20 is 5x. Divide by 5. Divide by 5. Cancel, cancel. 4. 120 is x. And we write a comment. So it becomes quite quick and fairly intuitive. Stratified sampling's not on the higher GCSE anymore, but they do imply it, and it has come up in an implied case like this where the proportion in a sample needs to be the same. So the words might not be used, but it's there. But we see there's 28 out of 70 is equal to x out of 900. We've got the same thing. 14 goes into 28 twice. 2/5 is x over 900. 2 times 900 is equal to 5x. Divide by 5. divide by 5, x is equal to 360. I've cheated there and looked at my answer. I didn't do that very quickly in my head, but I suppose it lends itself well to non-calculator work. I'm coming a bit towards the end. When we first adopted this method, it was discussed and quickly dismissed, but not because it wasn't good, just because we like the method of decimal multipliers. But I used to teach the unitary method of reverse percentages, and I would much prefer to do this now than the unitary method, although I still think decimal multipliers would be my preference. Sorry, after a 20% reduction, so I've got 80% left, so 80 out of 100. The toy is £16, so it costs, what was its initial price, so 16 over x. 8 over 10, 4 over 5 is equal to 16 over x. So 4x is equal to 16 times 5, divide by 4, divide by 4, x is equal to 20. So we then write our comment, £20. But we do not use this method now at Queen Mary's. We use the decimal multiplier method. We draw 2 boxes and we say that's times by 0.8. So the final one is 16. So 16 divide by 0.8 will give us our answer directly. So that is our preferable method, but it would work. And I would probably say it's tempting to use this method for that as well, because it would work and it's just another reaffirmation of it. So the things that I was hoping to do is to offer an alternative approach to teaching lots of topics. I've shown my terrible handwriting and my modelling, but hopefully you see how I might explain those to a class, and maybe that's something that you liked, or maybe actually you could think, that's something I won't do myself, and that's also a positive thing to come out of it. And this idea that when we have a method, we try and use and practice that method in as many different topics as we can, so we're consistent and the students learn a consistent approach.